In this experiment, we will be measuring the relative precision and accuracy of several pieces of laboratory glassware. The objective of this experiment is to determine the relative accuracy and precision of three common pieces of lab glassware: the beaker, the graduated cylinder, and the burette. Laboratory glassware is an important part of any chemistry experiment. Understanding its uses and limitations is important for success in lab. Generally, there are two primary uses for glassware in a chemistry lab. First, glassware is used to hold samples during experiments, including while chemical reactions are occurring. Second, some glassware is used to accurately measure and transfer liquids from storage vessels to reaction vessels. Most glassware is designed for either holding samples or for measuring volumes, but typically not for both. The three types of glassware that we will use all have demarcations or graduations indicating the volume when filled to the line. How true and reproducible the volume is depends on the type of glassware. As mentioned before, we will look at three pieces: a beaker, a graduated cylinder, and a burette. Before we discuss the glassware, we need a way to measure how true and reproducible the volumes are. Every measurement we make in the lab has two qualities associated with it: accuracy and precision. It is the goal of any measurement to provide the greatest degree of accuracy and precision possible. When we maximize these qualities, we are producing the best quality measurements possible. Accuracy is a measure of how closely individual measurements agree with the correct or true or expected value. Accuracy answers the question, how far off are your measurements from the bullseye? The closer the measurements are to the true value, the higher the accuracy. Precision, on the other hand, is a measure of how closely individual measurements agree with one another. Precision answers the question, how tightly grouped are your measurements? The closer together your measurements are, the higher the precision. As indicated before, we want to have the highest accuracy and the highest precision possible for our measurements. This means that all of our measurements are both close to the true value and close to one another at the same time. This is indicated by the upper left-hand image, where we have the golf balls all lying very close together and very close to the hole. This indicates good accuracy and good precision. The middle image on the right shows that the golf balls are all closely spaced together, but they're not particularly close to the hole. This indicates good precision, but poor accuracy. In the bottommost image, we see that the golf balls are all quite far apart, and none of them are particularly close to the hole. In this case, we have poor accuracy and poor precision. In most cases, we would like to have a mathematical value to account for both the accuracy and the precision, and it turns out we have one of each. The average of our set of measurements is a value indicating the middle of our set. It is calculated by adding up all of the measurements and dividing by the total number of measurements. We denote each measurement individually as x1 for the first measurement, x2 for the second measurement, etc. The average itself is denoted as the letter x with a bar above it. Mathematically, we can calculate the average of n measurements as the following form. X bar is equal to the sum of x1 plus x2 plus x3, so on to xn, all divided by n, the number of measurements. The closer your average value is to the true value or the value you expect to receive, the better or higher your accuracy. Let's consider an example. Suppose you and a friend are each asked to measure the mass of 3 different sugar cubes. In this case, our total number of measurements, capital N, is equal to 3. Each cube should have a mass of 4 grams. You pick 3 cubes and find the masses to be 4.103 grams, 4.098 grams, and 4.105 grams. Your friend picks 3 other cubes and finds the masses to be 4.075 grams, 3.978 grams, and 4.010 grams. First, we can calculate your average. This is just x bar is equal to the sum of 4.103 grams plus 4.098 grams plus 4.105 grams, all divided by 3, which is equal to 12.306 grams divided by 3, or 4.102 grams. Next, we can calculate your friend's average. In this case, x bar is equal to 4.05 grams plus 3.978 grams plus 4.010 grams, all divided by 3, which is equal to 12.063 grams divided by 3, or 4.021 grams. Note that your friend's data are more accurate than yours, because 4.021 grams is closer to 4 grams than your average value of 4.102 grams. Next, we have the standard deviation of our measurements, and this is a measure of how precise the measurements are. The standard deviation tells us how spread out the data are. The smaller the standard deviation, the greater the precision. The standard deviation, which is denoted lowercase s, is a bit more complicated to compute. First, we have to calculate the deviation, which is given the letter lowercase d for each measurement. Please do not confuse this with the density later on. The deviation is just the difference between the measurement itself and the average value. For example, the deviation for the third measurement is denoted d sub 3 and is equal to x sub 3 minus x bar. Once we calculate all of the deviations, we square each of them, add up each of the squares, and divide by n minus 1. Lastly, we take the square root. Mathematically, it looks like this. S is equal to the square root of the entirety of d1 squared plus d2 squared plus d3 squared, and so on to dn squared, all divided by n minus 1. Do not forget to take the square root after you do the division. So let's calculate the standard deviation of your masses. Recall that your measurements were 4.103 grams, 4.098 grams, and 4.105 grams, and that your average value was determined to be 4.102 grams. First, we calculate each of the deviations. D1 is equal to x1 minus the average, or 4.103 grams, minus 4.102 grams. This gives a value of 0.001 grams. D2 is equal to 4.098 grams minus 4.102 grams, which is equal to the negative of 0.004 grams. Finally, D3 is equal to 4.105 grams minus 4.102 grams, which is equal to 0.003 grams. Next, we square each deviation. Squaring D1, we get 0.001 grams squared, which gives 0.000001 square grams. We can continue with D2 squared, which is 0.000016 square grams, and finally D3 squared, which is 0.000009 square grams. At this point, we can finish the calculation. The first step is to sum all of our square deviations in the numerator and then divide by n minus 1, which is 3 minus 1 in this case. When we add up each of our square deviations, we get a value of 0.000026 square grams. divided by 2, or 3 minus 1. This gives us a value of 0.00000013 square grams, which we then take the square root of, giving us our standard deviation, which is equal to 0.004 grams. As homework, you should perform the calculation of your friend's standard deviation. You should find the value to be S is equal to 0.049 grams. Note that since her standard deviation is larger than yours, your data has a better precision than hers. Also, note that both the average and the standard deviation take the same units as the values you were originally measuring. In this case, everything has units of grams. We can now return to reading the volume of a liquid using our glassware. But before we do so, we need to be made aware of the fact that the surface of a liquid inside of a piece of glassware will generally not be flat. This is due to the interaction of the water molecules and the glass surface. Liquids such as water will tend to climb up the inside of the glass, causing a concave surface called a meniscus. When reading the volume of a liquid like water, we always read the marking at the bottom of the meniscus. In the figure to the left, we see that the major graduations on our glassware are each 1 milliliter wide. The liquid is lying between the 5 and the 6 milliliter markings. We look at our meniscus and we see that it is sitting just above one of the smaller markings. As there are 10 smaller markings in between 5 and 6, this indicates that each small marking accounts for 0.1 milliliters. The meniscus is sitting just above the 5.4 milliliter marking at the bottom. This indicates that our volume is approximately 5.4 milliliters. It is important to read the volume so that your eye is at the same level as the meniscus. Holding the meniscus above or below your eye level will result in a distortion of the reading, known as parallax. The first piece of glassware that we will use is called the beaker. A beaker is a wide, cylindrical piece of glassware that is typically used to hold liquids while stirring, heating, or other operations in the lab. Most beakers are graduated with markings, but the volumes are not typically very accurate and can vary by as much as 10%. If any reasonable amount of accuracy is needed, then beakers should not be used to measure volumes of liquids. We will demonstrate how poorly the accuracy and precision of a beaker measurement are. The second type of glassware is by far more accurate and precise. This is the graduated cylinder. A graduated cylinder is a narrow, tall cylinder of glass with etched graduations along the side. Because the graduated cylinder has a narrower column of liquid, and because they tend to be made more carefully than beakers, graduated cylinders will produce more accurate volume readings. Most graduated cylinders will report 3 significant digits. When we look at the graduated cylinder to the left, we note that the maximum volume we can record is 10 milliliters. This means that in general, all volumes using this graduated cylinder will be less than 10 milliliters. This provides us with our first significant digit. To obtain a second significant digit, we note that the fine graduations are located every 0.1 milliliter apart. When we look at the bottom of the meniscus in this case, this allows us to read the volume as being 6.5 milliliters with certainty. However, this is not the volume we record, as we will see in a moment. It is clear from the image that the actual volume is between 6.5 and 6.6 milliliters, and appears to be closer to 6.5 milliliters. It is customary to approximate the volume to 1 extra decimal place. This becomes the third and least significant digit. In the case of this figure, a volume of 6.51 or 6.52 milliliters should be recorded. It is expected that 2 different people will probably give a slightly different value. This is why the last digit is considered to be the least significant digit. The third piece of glassware to be used is a burette. The burette is a much longer, narrower cylinder with etched graduations like the graduated cylinder. Burettes are very commonly used to deliver accurate, sequential volumes of a liquid, such as in a titration. The top of the burette is open so that the liquid can be introduced. The bottom of the burette is fitted with a stopcock, which can be opened to deliver the liquid or be closed again. Common burettes can hold 50 milliliters of liquid and are graduated to 0.1 milliliters. As with graduated cylinders, you should read the volume to one extra decimal place. Here we see a diagram of a burette. One main difference between the burette and the other glassware that we use is that the markings are reversed. In the graduated cylinder, the zero marking is at the bottom and the maximum marking is at the top. With a burette, the zero marking is at the top and the 50 milliliter marking is at the bottom where the stopcock is. Please be aware that when we read the volume on a burette, we always read downward rather than upward. To fill the burette, you first add a burette funnel and then you pour in the liquid. We make sure not to attempt to fill the burette all the way to the zero marking. There are two reasons for this. One, it's oftentimes very hard to accurately read the burette when it's filled to the top due to parallax. Secondly, trying to get the liquid exactly at the 0.00 marking is a waste of time when we have other experiments to perform. In general, we will fill the burette approximately 3/4 of the way full with whatever liquid we're working with. Unlike the other glassware, we have to take 2 readings every time we use the burette, the initial volume and the final volume. In this case, the blow-up shows that the initial volume, where the meniscus lies, is below the 6 milliliter line. Since we are reading down, that means that our value will be greater than 6 milliliters. Each small marking is 0.1 milliliter, and therefore, when we read this, we will approximate it as 6.15 milliliters in our notebook. Let's suppose that we need to deliver 43 milliliters of liquid. In order to accomplish this, we first have to do a little bit of simple arithmetic. Since we're starting at 6.15 milliliters as our initial reading, we need to add 43 milliliters to this. This gives a final volume of 49.15 milliliters. It is our goal to drain the burette liquid until the meniscus sits exactly at 49.15 milliliters on the burette. We open the stopcock and allow the liquid to drain until it is as close to 49.15 milliliters as possible. When we look at the blow-up for our final volume, we see that we are not exactly at 49.15 milliliters, and that's okay. We record the actual volume from the burette. In this case, it should be recorded as 49.12 or 49.13 milliliters. To calculate the actual volume delivered, we then subtract the initial volume, 6.15, from our final volume, 49.12, and that gives us the total volume delivered. This brings us to the procedure for our experiment. The entire point of this experiment is that since we don't know how accurate and precise the 3 pieces of glassware are, we cannot trust the volume graduations. We need to determine which are accurate and precise. To do this, we will use the property called the density. The density is the ratio of the mass of a material to its volume, or mathematically, D for density is equal to M for mass divided by capital V for volume. If we can measure the mass of water, And if we know the density of water, then we can calculate the volume of water by inverting this equation, such that the volume is equal to the mass divided by the density. The density of a material changes as the temperature changes. And so you will record the temperature of your water, and you will find the density of water at various temperatures in a table in the experiment PDF posted on Canvas. The procedure will be very similar for each of the three pieces of glassware. You will begin by taking a clean, dry 50 milliliter beaker and weighing it empty. You will record this mass to 3 decimal places in your notebook. Using a wash bottle, you will then add water until the meniscus sits exactly on the 10 milliliter graduation of the beaker. At this point, you will reweigh the beaker with the water. The mass will now be larger than the empty beaker. You will then subtract the empty beaker mass from the mass of the beaker and the water. This results in the mass of the water. Then, using the density of the water at the proper temperature, you can calculate the actual volume you delivered. In the case of the beaker, it will likely be considerably less than 10 milliliters. You will then clean and dry the beaker and repeat this process 2 more times. Next, we will use the graduated cylinder. Again, we begin with a clean and dry beaker and record the mass of the empty beaker to 3 decimal places. You will then fill the graduated cylinder exactly to the 10.0 milliliter graduation. You will pour the water into the dry weighed beaker. At this point, you will reweigh the beaker and calculate the actual volume of water delivered by the same subtraction method. These values should be much closer to 10 milliliters. Again, you will clean and dry the beaker and repeat this process 2 additional times. Finally, you will use the burette. Once again, we start with a clean and dry beaker and record the mass. Close the stopcock on your burette and fill the burette about 3/4 of the way full with water. Make sure that the level of the water is above the 20 milliliter mark, or else you will not have enough water to complete the experiment. Begin by recording the initial volume of the burette to 2 decimal places, remembering to read down, not up. Then open the stopcock and drain the water into the dry beaker until you deliver exactly 10 milliliters of water. Be as careful as you can to get exactly 10 milliliters, but be sure to record the actual final volume from the burette, even if it's not exactly 10 milliliters. As before, reweigh the beaker and calculate the actual volume of water delivered using the subtraction method. This is now different than the other glassware. You will need to calculate the actual volume you delivered according to the burette. To do this, subtract the initial burette reading from the final burette reading. Now clean and dry the beaker, and you'll repeat this 2 more times. Do not refill the burette. Start from the same volume that you ended on for the previous run. Lastly, you will clean up your work area and your glassware. Please be sure to wipe down your entire work area with alcohol before leaving. This concludes this video. In the next video, we will walk through the calculations and discuss the report to be submitted in 2 weeks.